students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as oscillation. Now, we are going to see graphical representation of oscillation today. Let's see graphical representation of SHM. Let's see the graphical representation of SHM. Right? Now, how do I represent this with the help of a graph? Now, the three parameters that we are going to check is displacement, velocity and acceleration. Right? Case 1. When the SHM starts from mean position. If the SHM starts from mean position, the formula for displacement we have already derived. Displacement is equal to A sin omega t. Velocity is equal to A omega cos omega t. And acceleration is minus A omega square. Sin omega t. Right? Now let's try to see this. Let's first consider the phase omega t. Now what are the various values that omega t can have? Omega t can be 0, 90, 180, 270 and 360 degrees. Right? Let's consider displacement. Now, if I consider displacement A sin omega t, right? Now, before I do that, I'll just show you a rough form of this sin 0, 90, 180, 270, 360. Sin 0 is 0, sin 90 is 1, sin 180 is 0, sin 270 is minus 1, sin 360 is 0. Right? Now, since displacement is equal to A sin omega t, right, it has sine. Sine, if I consider omega t to be 0, sine of 0 is 0. Right, so A into 0 will give you 0. Sine 90 is 1. So this will be sine 90 which will be 1. So this will be A. Sine 180 is 0. Sine 270 is minus 1. So this will be minus A. And sine 360 is 0 again. So these will be my minimum and maximum values of displacement. Let's consider velocity. Velocity is given by the formula A omega cos omega t. Before I explain this, I'll just show you this working note. Cos 0 is 1, cos 90 is 0, minus 1, 0, 1. Right? Now let's see this. Cos of 0 is 1, so therefore this will be A omega. Cos 90 is 0, so this will be 0. Cos 180 is minus 1, so minus 1 into A omega will give you minus A omega. Cos 270 is 0, 360 is 1. Right? Next, acceleration. Acceleration is given by the formula minus A omega square sin omega t. Right? Now we know that sine of 0 is 0. If sine of 0 is 0, that means this will be 0. 90 will be minus A omega square. 180 will be 0. 270 will be minus A omega square into minus 1. That is going to be A omega square. And 360 is going to be 0. Now let's try to graphically represent this. First, let's see displacement. First, let's see for displacement. Zero, 90, 180, 270, 360, right? Sine of 0 is 0 and it varies between plus a and minus a. So sine 0 is 0, sine 90 is a, sine 180 is 0, sine 270 is minus a, and 360 is 0. Draw this graph. This is going to be my displacement curve. Fine, do we get this thing here? This is how the curve will look like. Next, let's draw the velocity curve. Now the velocity curve, let's draw 0 first. The velocity curve varies between a omega and minus a omega. This is a omega and this is minus a omega, right? So this is going to be 90, 180, 270, 360. Okay, let's see this. Now, sine of 0 is minus a omega. So it will start only from here, right? 90 is 0, 180 is minus a omega, 270 is 0, and 360 is again a omega. So the curve is going to be like this. This is going to be my velocity curve, right? Next, let's see the acceleration curve. Acceleration curve. Zero, 90, 180, 270, 360. Okay. Now it starts from 0. It's going to vary between a omega square and minus a omega square. A omega square and minus a omega square. Right? It is going to vary between 0, minus a omega square, then 0 again, then you have a omega square, and then 0 again, right? So this acceleration curve is going to be like this. This is going to be my acceleration curve. So these are going to be my displacement, velocity and acceleration curve minimum and maximum values. Fine, do we understand this? This is when the SHM starts from mean position. What if the SHM starts from extreme position, right? Let's see in SHM when the SHM starts from extreme position, case 2. Case 2, when SHM starts from extreme position. When SHM starts from extreme position, displacement is given by the formula A cos omega t, velocity is given by the formula minus a omega sin omega t, and acceleration is given by the formula minus a omega square cos omega t. Right? Now, let's first make the table for this. Phase is omega t. What are the various values? 0, 90, 180, 270 and 360. These are the various values that you can have. Displacement. Displacement is a cos omega t. A cos omega t. Right? Now we know that cos of 0 is 1. Cos 90 is 0. 180 is minus 1. 270 is 0. 360 is 1. So the values will be between a0, minus a0 and a. Next, velocity. Velocity is minus a omega sin omega t. Sine 0 is 0. Sine 90 is 1. Sine 180 is 0. Sine 270 is minus 1, so this will become a omega. And sine 360 is 0. Right? Similarly, acceleration. Acceleration is nothing but minus a omega square cos omega t. Cos of 0 is 1, so this will be minus a omega square. Cos 90 is 0. Cos 180 is minus 1. 270 0. 360 minus a omega square. Right? Now, once you have this, then let's see the graph. First, let's see the graph for displacement. Displacement graph is going to be between A and minus A. This is 90, 180, 270 and 360. Okay, now let's see this. 0 is A for displacement. 190 is 0. 180 is minus A. 270 is 0 and 360 is A again. Right? So the graph is going to be like this. This is going to be my displacement graph. Right? So the displacement graph is going to be this way. Fine. Next, let's consider the next graph, that is, let's consider the velocity graph. Velocity graph is going to vary between a omega and minus a omega and minus a omega, right? This is 90, 180, 270 and 360. Okay, now let's see this. 0 is 0, then 90 is minus a omega, 180 is 0, 270 is plus a omega and 360 is 0, right? Right? So in that case, this is going to be your velocity graph, right? And last, acceleration graph. Acceleration graph is going to vary between minus a omega square and plus a omega square. Minus a omega square, sorry, plus a omega square and minus a omega square. Right? Let's see this. 90, 180, 270 and 360. Right? Now this is going to be minus a omega square. This is your acceleration graph. This is going to start from minus a omega square, 0, a omega square, 0 and then minus a omega square, right? So in that case, this is going to be this. This is going to be my graph of acceleration. Fine, do we understand this? So do we understand how do we represent SHM graphically? This is your graphical representation of SHM both when it starts from mean position and when it starts from extreme position. Next, let's try to derive an expression for kinetic energy and potential energy of an SHM. Kinetic energy and potential energy of SHM. Right? Consider a body in SHM. O is the mean position, A is the positive extreme, B is the negative extreme. Right? Let's assume that the body has reached point P. body of mass m such that point P is at a distance of x from the mean position. Right? Let's write this much down. Consider a particle of mass m performing linear SHM along a straight line AB about mean position O. Right? In which case I can therefore say that let P be a point at a distance of x from the mean position. Let P be a point at a distance of x from mean position. Right? In which case I can say that the particle at P possesses both kinetic as well as potential energy, and the total energy possessed by particle at point P will be the sum of potential energy and kinetic energy. Now let us try to find out the kinetic energy expression for kinetic energy. Right? Now, when particle is at point P, when the particle is at point P, velocity of a body in SHM we have already derived as omega square root of a square minus x square. Right? That will be the velocity of the particle. And we also know, guys, that kinetic energy is equal to half mv square. Therefore, this is going to be equal to half mv square is going to be nothing but omega square a square minus x square. That will be the kinetic energy of the body in SHM. Now, let's find out the potential energy. Let us find out the potential energy. Now, a particle at point P is going to be acted upon by a restoring force. Particle at point P will be acted upon by a restoring force, and the restoring force is going to be equal to F, which is minus kx. That will be the restoring force that will act on it. Now let us assume that let the particle have a further small displacement of dx. Let the particle have a further small displacement of say dx. It is already at P. Let us assume that it moves in some direction, either towards the extreme or towards the mean position, and it has a small displacement of dx. Right? Now if it has a displacement of dx, let's assume that this displacement is done against the restoring force. The restoring force. Right? Now if there is displacement and there is force, then there is work. I can say let dW be the work done. In moving the particle. Now we know that work is nothing but force into displacement. So work is force into displacement. Now since work is done in a direction opposite to the force, the restoring force is acting towards the origin and the work or the displacement is towards the extreme position. Therefore this is going to be negative work. The negative sign indicates that force and work are in opposite direction. Substitute, but what is the value of F? F is nothing but minus kx dx. So this is going to be dw is going to be kx dx, right? Once I have this, then I can say that if this is the work done in moving the particle by a small distance, then the total work done in moving the particle from O to P will be W, which will be nothing but integral of the work done in moving the particle by a small distance, right? Which will be integral of dW. We found out is kx dx. You are moving the particle from where to where? You are moving the particle from O to P. That means you are moving the particle by a displacement of x, right? K is constant. Integral of x is nothing but x square by 2 when the limits are between 0 to x. So first you substitute the value of x with upper limit and then with lower limit. It is upper limit minus lower limit. So this will be k by 2 x square minus 0. So this is going to be kx square by 2, right? So that will be the work done. Now this work done is the potential energy of the particle. Work done is stored as potential energy in the particle. Therefore, I can say that the potential energy of a particle in SHM is half kx square. Fine, do we get this thing here? So we now know the potential energy and kinetic energy. Therefore, I can find out the total energy. Let us try to find out the total energy of a particle in SHM. Now the total energy of a particle in SHM is nothing but the sum of potential energy and kinetic energy. I can say that total energy is the sum of potential energy plus kinetic energy. Potential energy we found out as half kx square. Kinetic energy we found out as half m omega square a square minus x square, right? Now, but we know when we were deriving differential equation of SHM, we had said that k is nothing but m omega square, but k is nothing but m omega square. Therefore, I can say that total energy is equal to half. K can be written as m omega square x plus half m omega square a square minus x square, right? So this can be written as half m omega square. This is x square minus a square minus x square. Plus sign. So this is going to be half m omega square. Open the brackets. This is x square plus a square minus x square. Therefore, the total energy of a particle in SHM is half m omega square a square. That will be the total energy of a particle in SHM. Fine, do we get this thing here? So we have an expression for all. So that is kinetic energy, potential energy, and total energy. Fine, do we get this thing clear? Now, I can say that I can represent this way also. Since k is equal to m omega square, I can say therefore total energy is also equal to half ka square. The total energy of a particle in SHM can also be written as half ka square, right? I can also say that since you also know I can also say that omega is 2 pi n. So if I substitute in the equation of total energy, this will be half m. Omega is 2 pi n the whole square a square. This can be written as half m into 4 pi square n square a square, right? So in that case, this can be written as 2 pi square m n square a square, right? That is another expression for total energy. I am deriving total energy in different forms, right? One is half m omega a square, half m omega square a square. Second is half k a square. Third is 2 pi square m n square a square. I can say also frequency is nothing but 1 upon T. Therefore, total energy can also be represented as 2 pi square m a square upon T square. Right? Do we get this? So these are the different methods in which total energy can be represented. Right? From the above expression, we can say that from the expression of total energy, it can be said that total energy is A, directly proportional to the mass of the particle, is directly proportional to mass of the particle, it is directly proportional to the mass of the particle, is directly proportional to the square of the amplitude, directly proportional to square of amplitude, and third is directly proportional to the square of frequency. These are the three factors on which total energy of a body in SHM depends. Now, next, let us find out conservation of energy in SHM. Conservation of energy in SHM. If a body is in SHM, does it follow the law of conservation of energy? Now, by considering variation of kinetic energy and potential energy of a particle in SHM, we can derive this. Let's see this. First, consider a position of the particle anywhere between mean and extreme position. Position of particle anywhere between mean and extreme position. If the particle is anywhere between mean and extreme position, then I can say that kinetic energy of such a particle will be half m omega square a square minus x square. We have already derived this. Potential energy of the particle will be half m omega square a square x square, sorry, and total energy of the particle E will be nothing but sum of potential energy and kinetic energy, which again we have derived is nothing but half m omega square a square. This will be the kinetic energy, potential energy and total energy when the particle is anywhere between mean and extreme position. Next, let us assume that the particle is in mean position. Now when the particle is in mean position, the value of x will be 0. If value of x is 0, then what will be the kinetic energy possessed by the particle? It will be nothing but half m omega square a square minus x square, but x is 0. So kinetic energy of the particle will be half m omega square a square potential energy of the particle. When the particle is in mean position, this will be half m omega square x square. X square is 0. So potential energy of the particle in mean position is going to be equal to 0. Total energy. Total energy is nothing but a sum of potential energy and kinetic energy. So I can say that total energy is sum of kinetic energy plus potential energy, that is half m omega square a square plus 0, which will be half m omega square a square. Right? When the particle was between the mean and extreme position, even then the total energy was half m omega square a square. When the particle is in mean position, even then the total energy is half m omega square a square. Let's consider the particle in extreme position. If the particle is in extreme position, if the particle is in extreme position, then x will be equal to a, the total displacement will be a. In that case, the kinetic energy of the particle will be half m omega square a square minus x square. So this will be a square minus a square, that will be 0. The potential energy of the particle is half m omega square x square, that is going to be a square. Total energy of the particle is sum of the kinetic energy and potential energy, so which will come up to half m omega square a square. So whether the particle is between mean and extreme position, at mean position or at extreme position, the total energy is always half m omega square x square. This proves that energy is conserved in SHM. Right? So I can say whether the particle is between mean and extreme position or at mean position or at extreme position, the total energy is always equal to half m omega square a square. This shows that total energy is conserved in SHM. This is how you prove that SHM follows the law of conservation of energy, right? Irrespective of wherever the particle is, the total energy will always remain constant in it, right? Next, let us show graphical representation of total energy, potential energy and kinetic energy. Graphical representation of kinetic energy, potential energy and total energy. Right? Let's start. Now, you will have energy will vary between minimum and maximum value. Let's consider this to be my mean position O, right? Now, first let's draw the graph for, say, kinetic energy, right? I'm going to represent kinetic energy using a red line. Now, in mean position, guys, in mean position we have derived that kinetic energy is half m omega square a square. So in mean position, kinetic energy is maximum. At extreme position, we had derived that kinetic energy is 0. So at minus a and plus a, kinetic energy is going to be 0. So the graph of kinetic energy is going to be like this. This is my graph of kinetic energies, right? So this represents kinetic energy, right? Next, let's draw the graph of potential energy. I'll show potential energy with the help of black color. Now, in mean position, we had seen that potential energy is 0, and at extreme positions, potential energy is half m omega square x square. That means at extreme position it is going to be maximum. At extreme position it is going to be maximum. Right, now if I draw the graph for this, the graph for this will come out something like this. So what we see is that as kinetic energy starts increasing, potential energy starts decreasing. So this is my potential energy, right? Do we get this thing clear? And that is the reason why the line up there, this represents my total energy. This is my total energy. This is my total energy. Right? Do we get this thing clear? So this is your kinetic energy graph. This is kinetic energy. This is potential energy. And that is total energy. So graphically, that is how you are going to represent, and that is the reason why the total energy remains constant, right? So as kinetic energy goes on increasing, potential energy goes on decreasing. Right? Do we get this thing clear? So do we understand graphical representation of total energy, potential energy, and kinetic energy? Right? Okay, we'll stop this here for the day. Thank you very much.